Hi, and welcome back to my Physics Online video lecture series. Today's video, we're going to be doing a little bit more with the addition of vectors. This time, we're going to be focusing on how to add vectors in Cartesian coordinates. So this uses predominantly the algebraic method. I should note as a caveat at the start of this video that there is a bit of a difference between how we approach this in an algebra-based physics course and how we approach it in a calculus-based course. Now there's a bit of debate as to whether we should be approaching these two things differently, but this is kind of the standard way that algebra-based classes approach addition of vectors using algebra. I should say here that if you were to open up just about any textbook at random, and there are some exceptions I'm sure, but just about any textbook at random that's labeled college physics, algebra-based physics, general physics with algebra, trigonometry, AP physics, algebra-based, so high school AP classes as well. Every one of them, or almost every one of them, uses this method that I'm going to show. On the other hand, if you pick up a textbook labeled University Physics, Physics for Scientists and Engineers, Physics with Calculus, or some similar title, it will have a slightly different method that makes use of a thing called unit vectors. Now I'm not going to go into that debate today. And I'm not going to really talk about unit vectors today. Instead, I'm going to focus on this college physics, general physics, algebra-based physics approach to adding vectors, sort of the standard approach for algebra. You'll recall from the last video that I showed how to add vectors in polar coordinates using the tip-to-tail or geometric method. So that one basically works well for polar coordinates, and it works well for spherical coordinates, and it can work in other coordinate systems. So this tip-to-tail approach basically involves starting your first vector, then adding on your second vector, and then adding the third vector, and so on. And then your resultant vector begins at the beginning of the first and ends at the end of the last in the sequence. So the blue one that I've just drawn here, this would be my resultant. Or in other words, it would be A plus B plus C if these other three vectors represented respectively A, B, and C. Now this can be used, like I said, in Cartesian coordinates. So it can work, and it does work, in Cartesian as well. The problem is that in Cartesian, A, B, and C give you an X and a Y, and so instead of drawing 3 vectors with a ruler and protractor, you'd end up drawing 6 vectors. So if I were to show that, the steps would basically be to take the AX vector and draw it. So I would just draw a horizontal line, that would be my first one. Then I'd draw the AY vector, that would be a vertical line. Then I'd have to draw the BX vector, that would be another horizontal line. Then I'd have to draw the BY vector, another vertical line. Then I'd have to draw the CX vector, horizontal line, and then the CY vector, vertical line. And notice that I end up in the same location that I started from. Okay, so I've drawn these as AX, and then AY, BX, then BY, CX, and then CY. And then I would, again, draw my resultant from the start to the end. Although if I wanted to get the resultant in Cartesian, I basically have to draw a horizontal line for the resultant for X, and then a horizontal line for the resultant for Y. So this one right here would represent essentially AX plus BX plus CX. And this one right here would represent AY plus by plus cy. Okay, and so that actually does work. And actually, in some sense, this is the basis for how the algebra method works. And the reason why it's the basis is because you'll notice that I just added ax, bx, and cx here, and I added ay, by, and cy. So if I say, like, let this represent the resultant vector, r for resultant, then r, in this case, is representable by rx, comma, ry, where this one right here is my Rx, and this one right here is my Ry. So the algebra-based method basically involves doing exactly what I've done, but without drawing all the arrows. Because, as it turns out, we know what Ax, Bx, and Cx are, perhaps because they're given to us, and perhaps because we know how to convert from polar to Cartesian. So I've already made another video, obviously, for converting from polar to Cartesian. So let's put that under our recall. Recall can convert between bases. So can convert between coordinate systems. And what that looks like, I'll put it in 2D. And you can do it also in 3D, but for an algebra-based, we're going to stick with 2D for now. So these are your coordinate system conversion. We can convert Cartesian to polar. We can also convert from polar to Cartesian basically by making use of x is equal to rho cosine. I put a phi here, so I should probably make it a phi here as well. Rho cosine phi, and y is rho sine phi. So this one is how you would convert from polar back to Cartesian. You ultimately might want to use both of these conversions. Again, that's for another video. Today, the main point is we just want to get into the Cartesian system to be able to use this method. And for reference, if I have an x and y axis, like so, x and y axis, such that this is x and this is y, then my vector comes out to here, has a length rho, has an angle counterclockwise from the x-axis of phi, sometimes theta. This would be my x value, this would be my y value. Or in other words, this is a triangle of height y and base x. It's a right triangle. So now we say, what is this method for adding in Cartesian? Well, the first step is, per the previous slide page, whatever you want to call these, is to convert into the Cartesian coordinates. So convert all vectors to Cartesian. This is, of course, if necessary. So they may have started out in Cartesian to begin with. Sometimes they start in polar and you want to use this method. Okay. Second step, add all x's. So add all x's. This basically means resultant x will be this. So resultant x is this sum. That's another way of saying that Rx is equal to Ax plus Bx plus, if there are other terms, Cx, Dx, etc. The third step is to do the same, but with the y's. Add all y's. You could call this step 2a if you'd like. Resultant y is this sum. So we would have ry is ay plus by plus cy, dy, ey, etc. In 3D, you'd also have to do a fourth step of adding all the z's. Or maybe we could call this steps 2a, b, and c. So add all z's, resultant z is this sum. and I'll put, this is for 3D, of course. So your R sub z would be AZ plus BZ plus etc. CZ, DZ, etc. Step 3 basically is just put it together. So put it together. Basically, your resultant vector, let's do this, let's keep consistent here. R would be represented as Rx, comma, Ry, comma, Rz, this part being if applicable. And then a fourth step, also if applicable, would be convert back to your original coordinate system. So convert it back to original coordinate system. Again, that would be using this procedure on the previous slide if you're going from Cartesian back to polar. In 3D, you'd have to go from Cartesian to spherical or Cartesian to cylindrical. And that's it. That's the basic method. I am going to, in today's video, work a short example in which everything's already in Cartesian. So we're basically just looking at steps 2 and 3. A longer video could be made in which we start from converting to Cartesian and end with converting back to the original system. But today I want to do a short example. Alright, so in today's example we have 3 vectors A, B, and C. They're given in Cartesian coordinates. They appear to be displacements since the units are in meters. We want to find the resultant, which would also be sort of like the net displacement. So basically we would say that R sub x would represent AX plus BX plus CX. So what are AX, BX, and CX? Well, this would be AX, this would be BX, and this would be CX. Similarly, this is AY, this is BY, and this is CY. So I'm basically adding the first coordinate from each of these. So I have 5.0 meters minus 1.0 meters plus 4.2 meters. That should give me 8.2 meters. Okay, now I repeat the process for the y components using AY, BY, and CY. And so what that gives me is 3.0 meters plus 2.5 meters minus 4.1 meters, which should give me 1.4 meters. Now I put it all together to get my resultant vector in Cartesian coordinates, R, which would be represented by 8.2 meters, the x one first, or 8.2, comma, 1.4 in meters. And that's it. That's how we add in Cartesian. Hope you learned something, and thanks for watching.